Hi, welcome back to the ASHTO design procedure that is related to the rigid pavement. So far, we have covered last time quite a bit of details related to the rigid pavement design. So we talked about that we are covering the ASHTO 1993 rigid pavement design for which is based on the ASHTO. We're not going to discuss the PCA for the sake of this class. And we talked about the thermal serviceability as well as the initial serviceability and the delta PSI, and how is the PI, the initial serviceability here is 4.5 and instead of 4.2 for flexible pavement, but the thermal serviceability is the same table actually that we used for flexible pavements. Then we spent quite a bit of time dealing with the modulus of subgrade reaction. The modulus of subgrade reaction actually it required lots of corrections. We went through those last time. You got to ask yourself the first question whether or not you have a sub-base in the structure. If you do not have a sub-base, you're going to go with this simple equation right here. If you do have a sub-base, you're going to go through this graph, and we've covered it in much details last time, how to use the graph. And then the next question after having to check if we have a subbase or do not have a subbase is we need to check whether we have a rigid foundation or not. Having a rigid foundation was defined by a thickness of the subgrade less than 10 feet. If it's more than 10 feet, that means the bedrock is too far away and it's not going to have any benefit to change the K value accordingly. But if it's the bedrock is closer to the structure, then we're gonna give credit to that structure because the bedrock is so close, and we learned how to use this curve. And then we gone through the third question that we need to ask ourselves is how can we get the effective modulus of subgrade reaction based on the seasonal variation. And we got to learn again that somehow similar to what we've done for the flexible pavement, we need to use this equation to get the relative damage per month. And then we once we get that per month, you're gonna do it for all. You're gonna sum up all the damages, divide them by 12, get the average amount of damage, and then we're gonna reapply the same equation. But now the average damage will be known, the thickness of the PCC layer is known. The only thing that's not known in this case is the K value. And the last thing when it comes to correction was the loss of support and how this is basically determined by the type of material that we use. If it's a cement treatment or cement treated aggregates or asphalt treatment, the loss of support is very minimal, somewhere between 0 and 1. But if we have an unbound granular materials or even a fine grained materials, the loss of support would be significantly high, 2 to 3, and we got to know how to use this graph to reduce the amount of K as the final stage of the correction process that we learned last time. And we had a couple examples. I highly recommend you to go through those examples. They're very important and very informative as well. So this is here where we stopped last time. Again, well, this is the design equation, which is remind us with the equation for flexible pavement, but again, it has its own distinction. So W18, this is the amount of easels for the design life. ZR and S node, this is actually has to do with the standard deviation of the materials and the traffic and the deviation in general that has to do with the pavement, the rigid pavement, and of course the two of them together represent the reliability level. And then the D, this is the thickness of the required thickness of the PCC layer. And then we have the delta PSI, which is the thermal serviceability minus the initial serviceability minus the thermal serviceability. And then we have some new factors that I'm going to discuss in a little bit, which is SC prime, CD, J, EC, and sure enough, the K. So the K this is actually what we spent again the entire lecture of last time getting that K, going through all the steps. And that's why again we need it because it needs to be plugged in this equation, or instead of using the equation, we can use the nomograph, which again we're going to have a special nomograph for the rigid pavement design. Again, some of the terms that was introduced in the previous slide is SC prime. This is the modulus of rupture for Portland cement concrete. That is, again, that's used on a particular project. The J value, this is actually the load transfer coefficient that's used, and I'm going to explain it and have its own table, which is table 12.18. But the load transfer coefficient actually is used to adjust for load transfer characteristics of a particular design. If I have some dual bars that can transfer the load from one adjacent slab to the other, it has some, again, it has some coefficient. If there's not much of load transfer, it has another coefficient. CD, this is the drainage coefficient. For some reason, the AASHTO, when they moved from flexible pavement, they used to call it M, which is the drainage coefficient. For the rigid pavements, they call it CD, which is the drainage coefficient, and it has a table 12.20. And then EC, this is the modulus of elasticity for Portland cement concrete. So let's get going first with the J. J value, again, this is the load transfer coefficient that's used again to adjust for the load transfer characteristics of a particular design based on, again, looking into this graph, that the J account for the ability actually of a concrete pavement to transfer the load across the joints and the cracks. So we use, again, the use of that type of transfer, of load transfer devices, such as tie bar, or we can tie the concrete shoulders that will increase the amount of the load transfer, and of course that will decrease the J. So the lower the J, the better the design in this case. So let's take a look at this table here. It all depends on, first you can ask yourself, what type of shoulder are you going to have? Is it going to be an asphalt shoulder or a tight PCC shoulder? So again, here we're assuming that the main structure is already a rigid pavement. The question is, are we having a rigid pavement structure with an asphalt shoulder, or are we having a rigid pavement structure with tied PCC, tied Portland cement concrete shoulder? So that's the first question. Then you're going to ask yourself, what type of load transfer do we have? Is it, if there is any load transfer between an asphalt shoulder and the rigid pavement main lanes or not? Same thing for PCC shoulder. So sometimes we have, again, tie bars that can tie the shoulder to the main structure. So now the structure is one instead of having actually two pieces. So it depends if I have, again, if there is any load transfer or there is no load transfer. Next here is actually the pavement type itself. If first line here is for plain jointed concrete or jointed reinforcement, or the last or the second type is the continuously reinforced concrete. So the first category here, this is for both plain concrete or partially or reinforced concrete, but this one here is the continuously reinforced concrete. And of course, we would pick a number based on the case. So for example, if I have an asphalt shoulder and there was some sort of load transfer, and it was, the main structure is the continuously reinforced concrete pavement, you're going to pick a number from this range here, from 2.9 to 3.2. And as you can see, the best case scenario in this table is actually to have a tied PCC that with some sort of load transfer, and of course a continuously reinforced concrete. So this number right here considered to be the best case scenario, which is 2.3. Next is the drainage coefficient. Again, it looks very, the structure of the table looks very similar to what we've discussed for the M value, which is the drainage coefficient. But again, here it has its own table. So the quality of drainage, again, it's excellent, goes from excellence to good, fair, all the way to very poor. And this is here the percent time of the pavement structure exposed to moisture level that's approaching saturation. Again, if it's 1%, less than 1%, 1 to 5%, 5 to 25, or if it's more than 25% of the time that the rigid pavement structure is having to do or having to deal with saturated state. Next is the EC value, which is the modulus of elasticity for any Portland cement concrete. So the EC value can be estimated knowing the F prime C, which is the compressive strength. And so the compressive strength, the square root of this compressive strength times 57,000, that would get us the EC and PSI. So let's have an example so I understand now how can we put all this together. So the question here is asking us that using the AASHTO rigid pavement procedure, design a pavement for an urban interstate highway, urban interstate highway. The expected design ESL is 26 million. I mean, the pavement structure is to consist of a PCC with an elastic modulus of 5 million psi and a modulus of rupture SC of 650. And then we have a cement treated granular subbase with an elastic modulus of 1 million psi, which is insensitive to the season. That means which is a little bit different than what we discussed in a previous example, where the modulus of the subbase can or cannot change with seasons or with months. The pavement is also to be constructed as a jointed plain concrete with an asphalt concrete shoulder. Asphalt concrete shoulder. And then here is telling us that the climate consists of a wet season, which is from November to April. And then we have a dry season, which is from May to October. Freezing of the subbase and subgrade considered negligible, so we're not going to deal with that. And then the elastic modulus of the subgrade is having two values. So instead of going to the field sometimes and do monthly readings, we can have only two readings, one for the dry season and one for the wet season. Sometimes we do it by season or by 4 quarters of the year. So you're going to see again in the next couple slides that now we're going to deal with two numbers. So 5500 will represent all the elastic modulus or the dynamic modulus for the subgrade from the months of May to October, and MR, which is 45, this is for the wet season, which is going to be representing the months from November to April. There is another note here: there is no bedrock or other rigid material pavement, and that the pavement will be saturated about 25% of the time, and there is a good quality of drainage. This is going to help us to get the CD value. So let's get going here. The very first table, this is very similar, pretty much the same table that we use for rigid pavements. So for interstate, it was told it's an interstate and it's an urban setting, so it's 85 to 99.9%. So here again, I picked 95%. You can pick somewhere in between. Any range, any number between 85 to 99.9 will be acceptable, but I picked 95 in this case. And then we're going to talk about how can I get the delta PSI. The delta PSI is basically the initial serviceability minus the terminal serviceability. The initial serviceability is 4.5. This is again the default value for rigid pavements, brand new rigid pavements. And the PT, the terminal serviceability, it only depends on the classification of the roadway. So if you go back again to this example, it's actually interstate. So for interstate is the terminal serviceability determined by the table that I showed you previously is equal to 3. If it was a local street, it can be 2. Somewhere in between is 2.5. But in this case, the delta PSI would be 4.5 minus 3, and therefore the delta PSI is equal to 1.5. Let's note this is typical for rigid pavement. The standard deviation is a little less. There is a lot of less variability in rigid pavement compared to flexible pavement. So that's why the default value for the standard deviation for the Portland cement concrete structures are 0.35. Next, we need to pick the J value. The J value, which is again, this is the load transfer coefficient. It was told to us that the shoulder is gonna be an asphalt shoulder, and there is some sort of load transfer. So you will be told this in an exam or any other instant. You will need to know that yes, in this case, that there is a load transfer device, and it's I think it was jointed reinforced concrete. So the value would be 3.2. The J value, which is the load transfer coefficient, is 3.2. Next, we need to pick what is the drainage coefficient. The drainage coefficient, in this case, it was told in the problem, it's a good drainage coefficient, and we are going to handle about, let's revise and see here. We were told in the example, again, it's jointed plain concrete. This is again just to make sure, yes, we picked the right J value, but also, yes, it's the structure will be saturated about 25% of the time. So that number 25, this is what's going to trigger the value for the CD value. So here is from 5 to 25. So the drainage coefficient somewhere between 1 to 1.1. In this case, I picked 1. Next, now we need to determine the K value. Why do we need the K value? Again, remember in the equation here, again, we know what's the reliability level. I know what's the S node. I got to know the D is what I need to obtain. The E is provided to me. Delta PSI, we obtained it already. So the next step now is to get the K value. What's the K value for this structure? And that's actually what we learned entirely last time we talked about this chapter. So how to get the K value is, now we need to ask ourselves, what type of structure is this? Is it if there is a base, or there is no, if there is a subbase, or there is no subbase? In this problem there was a subbase, and we are asked now to design the structure. So if you recall, again, we have a PCC layer, I have a subbase, and then I have a subgrade. And in order to get the K value, if you recall, I need to know some information related to the thickness actually of the PCC layer as well as the thickness of the subbase. So how come the whole problem is asking me to design the thickness of the PCC layer and the thickness of the subbase, while before I get to that point, I need to get the K value first. And to get the K value first, you need to have an estimate, or what you need to have a known number for what's the thickness of the subbase and the PCC. That's why the unique process for rigid pavement here is actually start with an assumption. You're going to assume that the subbase thickness is this much, and assume the slab thickness is that much, and then you're going to go through the K value calculation, and then once we have all the input parameters, we're going to get to the nomograph or the equation. We're going to get the D value, which is the thickness, the required thickness of the PCC layer. If that matches what we assume, then great. If not, typically it's an iteration process. It's going to take us 2 to 3 iterations until we have the right answer. So bear with me here, but for now, let's assume that the subbase thickness is 12 inches, and the slab thickness, the PCC thickness, is 10. So I'm going to assume here that this is 10 inches, and here that this is 12 inches. Then now we need to get the value for the composite, the value for the K. So we're going to ask ourselves, and that's why again we're going to go all the way back to what we've discussed last time, is right here. So I'm going to ask myself, is this, I'm going to start with the first two cases here. Do I have a subbase or I do not have a subbase? In this case, I do have a subbase. Therefore, I'm going to follow case B. So to do case B, we need to follow this graph right here. That's why I will have, again, I'm showing you here that we're using this table quite a bit. So this is here what we have. So we need to use this graph. So how can I use this graph? As you know, again, I need to know first what's the subbase thickness, and that's the reason. Again, one more time, I hope now you link the dots together, that for the reason why I assumed the thickness for the subbase and the slab thickness, because I can't get anywhere without knowing that. So we start with an assumption that's 12 inches. So here's the 12 inches point, and then I went up and down. Where did I go up? I went up here to reach certain value for the subbase. How did I get the subbase elastic modulus? It was given to me from the example. Here you go. The subbase modulus is 1 million, and for the subgrade, it actually sometimes is 4,500, and some other times it's 5,500, depending on the season or depending on the month. So that's why I'm gonna do it twice. So for 12 inches, I went all the way up to the million, which is the very last line here. And then here again, I had 4,500 for the first run, and I do what we did last time, and now I pick the K value is 800. I do the same exact thing. Instead of now 4,500, I did it now for 5,500. That's why instead of stopping at this point, which is, again, if I were to draw a line here, this is the 4,500. Now I went a little bit down here to represent the 5,500. And I did the same thing. Notice at the top here doesn't change because it was told to us that the sub-base modulus doesn't change by season. So this is fixed. All what I'm changing is the modulus of the subgrade. So I'm going all the way one more time, and now I have a value of 1,000. So now we can construct this table right here. This table actually, this is for the months. I have again January, February, March, April, November, and December in one color because again I was told that the K value is constant from November till April. And I have another color for May to October because this is where the K value is a little bit different. So and this was all triggered by the value of the subgrade. You see here, they are all fixed. They're all the same, 4,500 from November till April. And once I get now to the dry season, the soil is getting stronger, so it's 5,500. While the elastic modulus for the sub-base is fixed, is 1 million. Now, this is the very first table, the first column that I filled based on this graph right here. I have 800 PCI for the weak month, and I have 1,000 PCI for the strong months. So that's why here I have 800 from November till April, and I have 1,000 from May all the way till October. The next question is, or the next correction for the K, if you recall, is do I have a rigid foundation or do not? In this case, I do not have a rigid foundation. I was told again there is no rigid foundation, therefore I'm skipping that. As you can see here, there's nothing. And then I move now to the seasonal variation. So I'm going to take this value all the way to here to get the relative damage per month. You don't have to repeat this for 12 times because the K value actually is just have two values. So it's 1,000 and it's from May to October, and that's going to trigger certain damage, relative damage for this month, which is 68. And we have for 800 we have a little bit higher damage, which is 76. So what to do with these numbers here? As I told you before, we need to sum up all these relative damages. So 76 1 2 3 4 5 6, so 76 times 6 plus 68 times 6, we'll sum them up. So the summation of all the relative damage is equal to 864. So we're going to divide the 864 to get the average relative damage per month, which is over 12. So on average, the average amount of relative damage is 72. So once we get this, we can get now the effective modulus of subgrade reaction using the same equation. Now I know that this is 72. The D here, remember the D here, the thickness of the PCC layer, which is again another reason why we had to assume a thickness for the PCC layer. In this case, I believe we assumed that it was equal to it was equal to 10 inches. Yes, 10 inches right here. So once I know that this is 10 inches and UR here is 72, the only unknown in this case would be the K value, and this is what we got here. The K value based on the effective modulus of subgrade reaction is 900. The last correction to do has to do with the K value as the loss of support. I was told that the loss of support equal to 1. So I would go now from 900 all the way up to the loss of support that's line that's correspond to loss of support equal to 1, and therefore the K infinity equal to 250. So this is the number where I'm gonna need for my design. So this is here the number that I'm gonna need, which is 250, based on my assumptions that they may or may not be close to the reality. That's why I like first here to now summarize all the numbers that I'm gonna need for my nomograph. So I have here the K infinity, which is 250, the SC prime, this is the modulus of rupture, 650 psi, S node This is the standard deviation is 0.35. Delta PSI, which is the difference between the initial serviceability and the terminal serviceability. So it's 4.5 minus 3, that's 1.5. And then I have the easels for this lane. So again, it was given to us in this example here per lane, so it's 26 million. Again, I'll be very explicit in an exam or in a homework, so don't worry about that. But in this case, let's assume that this amount of easels is 26 million for this lane. And then EC, this is the elastic modulus of the concrete, 5 million psi. The J value, which is the load transfer, is 3.2. The reliability level is 95%, and last but not the least is the drainage coefficient equal to 1. So once we have all these, welcome now to the nomograph. The nomograph here is actually a 2-page nomograph. So this is the first page of it. I'm going to walk you through it, and then we're going to move on to the next. So let's start. Where to start on this nomograph? Please bear with me here. So the very first step, as you could see, is from the left. It's actually the effective modulus of subgrade reaction. I hope by now, again, you know why it's important that we spent the last lecture talking about the k-value correction, because this is the very first step that influence the rigid pavement design. So it's 250. Once you pick that, the k-value here is 250, you're going to go all the way up, as you see, and then you are going to pick one of these lines. What are these lines represent? These lines represent the concrete elastic modulus, which was, in our case, it was 5 millions right here. So that's why here we stop at the line that says 5. So at this point right here. Then once you hit that point, you're going to draw a horizontal line. So you hit the 5 right here. And then you're going to draw a horizontal line. And then from there, you're going to connect this point to the next line right here. This line here, this is the mean concrete modulus of rupture, SC prime. SC prime, in our case, it was SC prime, it was 650 right here. So that's why we are connecting this point with 650. This is 700, this is 600, so it's in the middle until you hit this point, which is a turning line, similar to what we've dealt with for the flexible pavement. Once you hit this point, now we're going to connect this point to the next column, which is this is the load transfer, the J value. The J value was, if you recall, the J value, which is right here, this was 3.2 from table 1219. So I'm going to connect it again to the J value at 3.2 to hit the next turning line. Then from this turning line, we're going to connect it now to the CD value, which is the drainage coefficient. I remember this one, it was 1. So I'm going to connect this to the CD value all the way to the match line, another match line. So in this case here, the match line was roughly about 69. You're going to take this number, which is the match line, and then you're going to now go to the second page of that nomograph. So this is where you left off from the previous page of the nomograph, 69. Now we're going to connect it to the design serviceability loss, which is delta PSI. In this case, again, it was 4.5 minus 3, so it's 1.5. You're going to connect it to 1.5. And then you're going to stop here for a second, and then you're going to pick up from the bottom of this nomograph. This is here the reliability level. The reliability level was 95% right here. Then you're going to connect the reliability level to the standard deviation, which was 0.35 to hit the turning line. And then from the turning line, which is right here, you're going to connect it to the easels. This here represent the easels. Let's try to remember what was the easels. The easels, with this case, was 26 millions. So the 26 millions, you're going to connect it now to 26 millions. From this point here, you're going to hit this graph. So this graph, now we're going to connect these two together until you reach this point. What's this point really represent? Or what are these lines represent? This line represents the design of the slab thickness. What's the thickness needed really for this structure? So the thickness here in reality is 12.5 inches. We need 12.5 inches. Now you're going to ask yourself, what did we assume? So if you recall, our assumption for the PCC layer, it actually was not 12 inches. It was far away from 12 inches. It was 10 inches. We assume 10 inches instead of 12 and a half. What does this mean? We need actually now to repeat our calculations. Again, so instead of 10, it's going to be 12 and a half. What is the only thing that's going to change doing really another iteration is the K value, because the K value is going to change. And that's what we have here. So the required slab thickness is 12 and a half inches, not 10. The K value was determined based on the slab thickness of 10 inches. So this must be recalculated. And now we're going to assume that the slab thickness is 12 and a half instead of 10. Someone may ask, how about the thickness of the subbase? Typically, the subbase now doesn't change. Once you assume certain thickness, that doesn't change. All what you need to do during the iteration process, you're gonna redefine or refine your design to know the exact required thickness of the PCC layer, which is the most expensive layer anyways. But again, so if you have that question in mind, yes, when we design the PCC structure, we assume certain thickness of the PCC layer, we assume certain thickness of the subbase. The subbase doesn't change, it's going to be fixed, but with the iterations, we need to keep changing the thickness of the PCC layer. So what does this going to impact? It's going to impact actually this column right here only. Because again, you're going to repeat the entire table one more time. The composite K value doesn't change. Why it doesn't change? Even if we're changing the projected slab thickness now to be 12 and a half, because we fixed the thickness of the base. The base was 12 inches. Therefore, if you recall, the table to get the composite K for the first step only depends on the thickness of the sub base. Doesn't depend on the thickness of the PCC. So again, and I'll go back with you one more time so I will remind you. Here we go. So this table right here, it only depends on the sub base thickness, and if I'm fixing it, it didn't change from the previous iteration to this iteration, therefore I'm not going to repeat it. What's going to change though is the seasonal variation, the amount of relative damage, because that highly depends on whoops. Let's come back to here. So we're gonna repeat these steps again. So here, this is not gonna change, but what's changing now is the relative damage. Why the relative damage now is changing? Because the relative damage actually depends on this equation right here, and this equation actually doesn't it doesn't stay as is, because now the D, this is the thickness of the PCC layer. We for the first iteration we assumed it's 10, but now it's 12 and a half. That's why we're gonna repeat the damage accordingly. So now the amount of damage is the summation of all the months is 2082. The average damage now per month is actually 2082 over 12, so it's 173 and a half. And let me show. So this here, this is the average damage. You're gonna plug it into here. I have now this amount of average damage per month, I mean, is constant, which is 173.5. And then the D now is not 10 inches, what we assumed in the first iteration. Is actually now is 12 and a half. This is here 12 and a half. Please take note of that. And then now the corresponding K is actually 893. See? So it's changing. So 893 now, I need to go to the next step to correct that number based on the loss of support equal to 1. So 893, I'm going to go all the way up to get now the final K is actually 240. So if you recall, the first iteration it was 250, so we're getting closer to the real number. So now it's 240. Once we have the K values equal to 240, I'm putting now everything back together again. So the K40 is the K is 240. Everything else is the same. SC prime is 650. S node is 0.35. Delta PSI is 1.5. The amount of ESO is 26 million. The reliability level is 95%. The drainage coefficient is 1. The J value is 3.2. And the elastic modulus is 5 millions. So what you need to do now, we're going to go through and that's what I want you to do. We're gonna go through the nomograph one more time, and instead of 250, now it's gonna be 240. And as you're gonna go through this process, you're gonna see now the required thickness is gonna be the same. So once you have a constant thickness, you started now with this iteration is 12 and a half, and if you do the calculation, and if you do, I mean, if you go through the nomograph, you're gonna end up with about 12.4, 12.3 inches, which is about the same. So once you come up to this divergence, so typically you're going to ask me when should I stop doing more iteration. Once you are having now the difference between the last two iterations should be around zero point 0.5 inches. Once you arrive at that, then you are good to go. With that, again, we finish actually this chapter. I hope again it was informative. If you have any question, please reach out to me. Thank you so much. Bye bye.